Welcome back to the deep dive. Today, we are cracking the code on a feature so essential to the modern internet that honestly, we probably all take it for granted: autocomplete. It's that tiny text box, the one that seems to read your mind, offering suggestions the millisecond your finger even thinks about hitting the keyboard.
Yeah, it's absolutely ubiquitous. People call it type head, or maybe search as you type, incremental search,
Yeah,
lots of names. But for us, for system architects, this one feature, it's actually one of the most brutal scaling challenges out there.
right.
We're talking about designing the top K search autocomplete system.
Yep.
And that K is key. For today, let's say K is 5. So we need the 5 best suggestions ranked by how popular they are historically, and we need them, well, instantly.
Instantly is the word. So our mission today is really to understand the complex kind of multi-layered architecture that makes big systems like Google or Amazon search feel so instantaneous. We're diving deep into how architects make these choices, how they turn this just overwhelming amount of traffic. And we're talking billions of inputs into a super lightning-fast user experience. And importantly, based strictly on historical frequency, right? Popularity.
That's the core constraint for this first pass, yes. Historical popularity only.
This isn't just theory for you listening. This is like a shortcut to understanding the real trade-offs you have to make to build and maintain these massive, high-performance web services.
Yeah, definitely. We're going to walk you through the whole engineering process. Start with the scale, which is honestly mind-boggling, and then get into the specialized data structures you absolutely need to overcome that scale. Hashtag establishing scope and scale.
Okay, so let's unpack this. Like with any good system design problem, we need to start with some ground rules. Constraints, right? They say constraints force innovation.
They absolutely do. You need them to define the problem clearly.
So what are the constraints we're putting on this initial system, the ones that help us hit that speed target first and foremost?
Okay, so we start simple, or, well, simpler. First, big constraint, prefix matching only.
Meaning?
Meaning, if you type DOG, we can match dog food or dogmatic, but we do not match hot dog. The match has to be right at the beginning of the search query string. No mid-string matches for now.
Got it. Start simple, and what about the output? What do we actually return?
Strictly defined. Exactly 5 suggestions, so K5. And crucially, they have to be ranked solely by historical query frequency.
Popularity. Pure and simple.
Pure and simple. We're not doing any fancy personalized ranking yet, no location boost, none of that. Just a straight-up popularity contest based on searches people have done in the past.
Okay, and the input itself. Any limits there?
Yes, another simplification. For this first design, we're assuming input queries are only English and only lowercase alphabetic characters.
Ah, okay, so no capitalization, no numbers, no special characters.
None of that. And critically, no complex stuff like spell check or autocorrect. Not yet. We want this system to be incredibly lean, incredibly fast out of the gate, strip away everything non-essential to speed.
And all these constraints, they really exist to serve one master, don't they?
Absolutely.
The speed imperative. This
Yeah.
is the non-negotiable. And I want to emphasize just how tight this is. You're saying results must come back within 100 milliseconds.
Must. Yes.
Why that specific number? Is it arbitrary?
Not at all. It comes from hard-won experience from research done at massive platforms, like Facebook, for instance. They found that if that response time creeps over 100 milliseconds, the user actually perceives lag.
They feel it.
They feel it. The search bar feels like it's, stuttering. It's not smooth. So hitting 100 meters means the entire round trip, keystroke travels, server lookup happens, results come back, browser renders them. The whole thing has to feel practically instantaneous.
Wow.
If we miss that metric, honestly, the system's kind of unusable. It doesn't matter how good the suggestions are if they arrive too late.
That is just a brutal requirement.
Okay.
So to handle that, the architecture has to be spot on. But before we even talk solutions, we need to grasp the sheer scale of the problem we're facing. Hashtag tag back of the envelope estimation, the scale problem.
Right. Let's try and put some numbers on this. Back of the envelope time. Let's start with a reasonable assumption for a pretty big web service.
Yeah.
Say 10 million daily active users, or DAU.
Okay, 10 million DAU.
And let's say the average person performs maybe 10 searches per day. Seems reasonable.
Okay, 10 million times 10. That's 100 million searches per day. That sounds like a lot, but maybe manageable.
Well, let's look at the data size first before we get to the traffic. If we assume standard ASCII encoding, 1 character per byte, maybe a query is around 4 words, 5 characters a word, so roughly 20 bytes per query string.
Something like that, yeah.
So 100 million queries times 20 bytes. That's about 2 gigabytes of raw query data coming in every single day.
Okay, 2 gigs a day still feels sort of doable with modern storage, but here's where it gets tricky, right? This is where the architecture starts to really, sweat. The insight about the traffic multiplier.
That's the killer. Exactly. You hit search, you think you sent one request. Nope.
Right, you're sending a request for every single character you type?
Every single one. So if you type, like you said, DINER,
That's 6 requests, bam, 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 hitting our servers.
it's a fist request right there. And people aren't perfect typists, right? They backspace, they pause, they look at the suggestions, they change their mind, they keep typing.
Yeah, you hunt and peck or rethink mid-word.
So we have to make a conservative estimate. For every completed search someone actually runs, they've probably triggered something like maybe 20 incremental requests on average.
20 requests for one search.
At least.
Yeah.
That's the traffic multiplier. And that's what just absolutely destroys simple database solutions.
Okay, let's do the math on that then. 10 million users, 10 searches each, times 20 requests per search.
That gets us to 2 billion requests per day.
2 billion requests a day.
Okay.
Divide that by the number of seconds in a day. What's that work out to in QPS? Queries per second?
It comes out to an average QPS of around 24,000. 24,000 queries hitting our system every second, on average.
On average. But averages lie in system design, don't they? We need peak load.
Always designed for peak.
Yeah.
Exactly. Peak load, maybe during prime time, evening hours, big news events. It could easily be double the average. Let's say a peak factor of 2.
So that brings our peak QPS to roughly 48,000.
48,000, roughly.
Wow, okay. 48,000 incoming requests every single second at peak, and we have to answer each one in under 100 milliseconds?
Yep, yeah, that's the challenge.
48,000 simultaneous, lightning-fast lookups. Okay, yeah, now I really see why you said a traditional database approach is basically dead on arrival.
Completely infeasible for the query part, yeah. And we also can't forget storage growth. Let's say maybe 20% of those daily searches are totally new strings, queries we've never seen before. That's 20% of the 100 million completed queries times 20 bytes. That works out to about 0.4 gigabytes of new data we need to add to our searchable storage pool every single day.
0.4 gigs a day. So over a year, that's hundreds of gigabytes, easily, of just historical query strings we need to search through efficiently.
The scale is significant on all fronts: traffic, latency, and storage. Hashtag high-level design and the need for optimization.
All right, the scale is crystal clear. 48,000 peak QPS, 100 meters latency. That forces some serious architectural decisions right from the start. We need to structure this logically. Hashtag tag the two-part architecture.
Yeah, given those demands, the first thing we do is institute a separation of concerns. Yeah. Big time. Our system basically gets split into 2 massive, largely independent services.
Okay.
Think of it like, I don't know, the factory that builds the engine and then the car that uses the engine instantly.
Okay, I like that. So the factory.
The factory is the data gathering service. This is the back-end beast. It does the heavy lifting. Tracking, counting, aggregating, processing those billions of user inputs, figuring out which searches are actually the most popular over time.
And we'll quickly realize this part can't be real time, right?
Oh, absolutely not. We'll get into why, but yeah, that's a batch job. And then the car, the part the user interacts with directly.
That's a query service.
The query service. And this thing needs to be brutally fast. It gets a prefix like DIN. And its only job, its sole job, is to return the top 5 most frequent terms for that prefix in less than 100 milliseconds. End of story.
Focused, fast, specific. Hashtag tag the initial query service approach. The bottleneck.
So let's imagine you're a new engineer tackling this. The simplest thing you might think of first is, well, just use a database, right?
Yeah, seems logical. Just make a table, 2 columns, query string, frequency count, an integer. Done.
Exactly. That's the intuitive starting point. And honestly, for a small data set, low traffic, it works fine. You could run a simple SQL query. Something like, select query from frequency lightable, where a query like 200% order by frequency limit 5. Find all queries starting with TWD, sort them by frequency descending, grab the top 5.
Seems straightforward enough. You find the matches using using order by, you limit with limit. What breaks? Why is that the bottleneck?
It breaks spectacularly at scale. 2 main reasons, both tied to the massive size of that frequency cladle. First, the like prefix percent part.
The wild card at the end.
Yeah. That often prevents the database from using its standard super-fast indexing techniques that work great for exact matches. It might have to scan large portions of the table, or at least large portions of an index, just to find all the strings starting with that prefix. That's already slow.
Okay, so the lookup isn't as fast as we'd like, but maybe indexing helps a bit. What about the sorting?
That's the second, and usually the fatal flaw, the order by frequency DS clause. Let's say your like query somehow manages to quickly identify, I don't know, 100,000 queries that start with twin. The database then has to potentially pull all 100,000 of those records into memory, or at least handle pointers to them, and perform a sorting operation on that entire massive set, just to pick the top 5.
Ouch. Sorting 100,000 items just to get 5.
Exactly. That sorting complexity, which can be something like n log n, depending on the algorithm, combined with potential locking issues on a relational database getting hammered with 48,000 requests a second. It guarantees, absolutely guarantees, we will blow past that 100 millisecond target, probably by orders of magnitude.
So it's the sheer volume of potential matches for common prefixes and the cost of sorting them on the fly that just kills the standard SQL approach.
Completely. We need a data structure where finding prefixes and getting ranked results are inherently fundamentally faster operations, not something bolted on top like order by Y. Hashtag deep dive into the Trie data structure.
Okay, so the database is out for the query service. This leads us, I assume, to the specialized weapon of choice for this kind of problem.
It does. It leads us to the Trie, sometimes called a prefix tree or digital tree. It's really an elegant solution designed specifically for rapid string retrieval operations, especially prefix-based ones. Hashtag why the Trie.
The name itself, Trie, pronounced try, apparently comes from the word retrieval, which is exactly what we need. So how does this structure work? Why does it succeed where the relational database just failed so badly?
The magic is how it leverages shared prefixes structurally. Imagine a tree. The root node represents an empty string. Each node down from the root holds a single character.
Okay.
And the path from the root down to any node in the tree spells out a prefix. So to represent the word car, you'd have a path. Root C node, A node, R node.
Right, and then if you also need to store cat.
You reuse the path. Root CA is already there. You just add a new branch from the A node to a T node.
Ah, okay. So unlike, say, a hash map where car and cat are stated completely independently, the trie is optimized for sharing those common starting letters.
Precisely. That prefix sharing is inherent to the structure, which is perfect for autocomplete. Now, the basic trie just tells you if a word exists. To meet our requirement, we need to enhance it.
We need the popularity, the frequency.
Exactly. So we add frequency information right onto the nodes themselves. When we traverse down to the node that marks the end of a complete word, like the R in car, that node doesn't just signify the end, it also stores account how many times car has been searched historically.
Okay, so the data structure itself now handles two things: efficient traversal down the prefix path and storing the frequency metric we need for ranking right where we need it. Hashtag the initial trie algorithm and complexity.
So let's walk through the basic algorithm using this frequency-enhanced trie. How do we find the top K suggestions? Let's stick with K5 and say our prefix is inter.
Okay, step 1. Find the node that represents inter. We walk down the tree. Root INTE-ER.
Right. The time complexity for that is proportional to the length of the prefix. Let's call prefix length P. So finding the node is O.
And since we already talked about prefixes usually being short, maybe max 50 characters, OP is pretty fast. O50 is basically constant time for a computer.
Effectively constant time, yeah. So step 1 is fast. Now, step 2, once we're at the inter node.
We need to find all the actual search queries that start with inter, so we have to explore the entire subtree below that er node, right?
Exactly. We have to traverse every branch downwards from inter to find all valid completed words and grab their frequencies. Maybe we find internet with frequency 5,000, international with 1,000, interview with 800, maybe 50,000 other words.
Uh-oh. So the complexity of this step depends on how many children or descendants that prefix node has.
Precisely. Let's call the number of valid children, or completion C. The complexity of traversing that whole subtree is OC, and C could be huge for common prefixes.
Okay, that sounds like a problem. And then step 3.
Step 3, sort the children and get the top K. We take all those C results, we found those 50,000 words, and their frequencies, we sort them all by frequency, descending, and then we just pick the top 5.
And sorting C items, that's typical OC log C complexity, right?
Correct. So the overall complexity for this initial trie approach is OB for finding the prefix node, plus OC for traversing the subtree, plus OC log C for sorting the results.
So OP plus OC plus OC log C. You said earlier this is still too slow. Why? The tree seems so promising.
It's promising, but that OC and OC log C dependence kills us again. If C is small, like if you type intergalactic, maybe there are only 10 results, then it's lightning fast.
What?
But if you type a really common prefix like A or the or as, the number of completions C could be in the millions. Traversing millions of nodes and then sorting millions of results, OC log C takes way, way too long. We're right back to the same bottleneck that doomed the SQL approach. Unpredictable, potentially massive processing time based on the popularity of the prefix. We'll miss 100 meters easily.
Okay, so we have to get rid of that dependency on C. We need to somehow make the lookup time constant, regardless of how many millions of words start with A. We need O1, hashtag achieving O01, search time through optimization.
Exactly. Achieving O1 complexity, constant time lookup, meaning getting the results, takes roughly the same tiny amount of time whether the prefix is A or anti-disestablishmentarianism. That's the holy grail here. That's the core architectural leap needed for high-performance autocomplete.
So how do we do it? What are the optimizations? You mentioned two key ones.
Okay, optimization number one is kind of simple but necessary.
Yeah.
Limiting prefix length. We already touched on this.
Right. Users rarely type super long queries before clicking a suggestion.
Exactly. So we can realistically cap the maximum prefix length P we even bother searching for. Maybe it's 50 characters, maybe less. By setting a constant maximum P, the first step, finding the prefix node, becomes effectively O1, constant time.
Okay, that hand is the OP part makes sense. But how on earth do we get rid of the OC and OC log C? How do we eliminate the traversal and sorting time? That seems like the real magic trick.
It is the magic trick, and it comes with a significant cost. This is the crucial optimization. Cache top search queries at every node.
Wait, cache them. You mean instead of finding and sorting the children when the user searches?
We pre-compute them. We figure out our top 5 most popular queries that exist under each node in the trie, and we store that pre-sorted list directly on the node itself.
Hold on. You're saying every node in the trie, like the node for I, and the node for in, and int, and in, and inter. Each one holds its own list of the top 5 completed queries you can reach from that point downward.
That's exactly what I'm saying. Let's take a simpler example. The node representing the prefix B. It doesn't just know it's E and maybe its own frequency if B is a word. It also stores a small pre-sorted list. Maybe that list is best. 35, bet. 29, B. 20, B. 15, beer. 10.
Wow. So if a user types B, then E, the query service just traverses to the B node.
Finds that node, reads the pre-computed, pre-sorted list attached to it, and just returns that list instantly.
Okay. The implication is huge. If the top 5 results are already calculated, sorted, and just sitting there waiting, then the final step to get the top K becomes
Constant time, just grab the list.
we've completely eliminated the time complexity related to C, the number of children. The traversal, OC, and sorting steps vanish from the query time calculation. The entire lookup becomes O1 plus O1 equal 1.
We did it. We achieved constant time lookup.
Yeah.
But you have to ask the question, right?
I was just about to. What's the catch?
Yeah.
This sounds incredibly expensive in terms of memory. We're taking this potentially large trie structure and making it vastly larger by storing lists of strings, the top 5 queries, on potentially millions of intermediate nodes. Are we just trading time complexity for insane space complexity?
That is the classic space-time trade-off right there. Yes. We are absolutely sacrificing potentially massive amounts of memory.
How much are we talking?
It depends heavily on the vocabulary size, the average length of query strings in pants K. But yeah, the overhead for storing those cache top P's life on every node can be substantial. We could easily be talking hundreds of gigabytes, maybe even terabytes, of RAM needed to hold this entire optimized trie structure in memory across a cluster.
Terabytes of RAM just for autocomplete suggestions.
But think back to the requirement. The system is unusable if it's slower than 100 milliseconds. So this sacrifice, this massive memory footprint, is deemed necessary. Speed is the absolute #1 priority. We buy that speed with memory. Lots of it. #tag designing the scalable data pipeline.
Okay, so we've designed our Ferrari engine, the O1 query service, based on this memory-hungry optimized trie, but now we need the factory. We need the system that actually builds this giant trie, complete with all those cached top lists, without crushing our resources or interfering with the live service. #tag transitioning from real-time to batch processing.
Right. And the first, most critical realization for the factory, the data gathering service, is that trying to do this in real time is a non-starter.
You mean trying to update the trie structure with every single search query as it comes in, all 48,000 per second?
Exactly. System suicide. Think about it. For every query, you'd potentially update frequency counts on multiple nodes. Then, you'd have to check if that change affects the topco list on that node. If it does, you have to update the list. Then you have to go to the parent node and see if its topco list changes because its child's list changed.
All the way back up to the root.
All the way back up. The amount of locking, computation, and potential write contention across the entire trie structure would be absolutely enormous. It would consume insane resources and almost certainly slow down the read requests, the ones that need to be O1.
Plus, let's be realistic, the top 5 most popular searches for intention probably don't change every 5 seconds.
Exactly. Top queries tend to have inertia. They change, yes, but usually not that rapidly. Maybe over days or weeks, unless there's a huge breaking news event, which we'll talk about later.
So this relative stability is key. It allows us to move away from real-time updates for the main structure.
It allows us to embrace batch processing. We accept that the trie won't be perfectly up to the second, but instead we'll rebuild it periodically using data collected over a longer interval.
Where does that data come from?
It comes from our standard analytics and logging services. These are the systems already in place that record user activity, including every search query performed. We basically tap into those logs.
And how often do we rebuild?
For general-purpose search autocomplete, like we're designing, a weekly rebuild is often a good starting point. It's frequent enough to capture meaningful shifts in popularity, but infrequent enough that the massive offline computation is manageable. #tag components of the new data pipeline.
Okay, batch processing it is. Let's trace the flow of data for this weekly rebuild. Where does it start?
It starts, as I said, with the analytics logs. These are just huge, raw, append-only files or streams. Timestamp, user ID, maybe anonymized, the query string itself. Just a fire hose of data.
Potentially petabytes of data, right?
Oh, easily, for a large service. And because of that sheer volume, this is often the first place we need to think about optimization, specifically data sampling.
Sampling. You mean we don't even process every single logged query?
At very large scale, maybe not. Especially during peak hours, we might implement a rule like only log or process 1 out of every n requests, maybe 1 in 10 or 1 in 100.
Doesn't that hurt the accuracy of our popularity counts?
Surprisingly, not as much as you might think for ranking purposes. As long as the sampling is random and consistent, the relative frequencies usually remain statistically representative. It gives you a very good picture of what's popular overall, while drastically reducing the amount of data you need to store and process later. It's a cost-saving measure.
Okay, so we have potentially sampled raw logs. What's next?
Next come the aggregators. Their job is to chew through these massive logs from the defined period, say the last week, and condense them. They basically count things up. They process terabytes or petabytes of raw log entries and distill them down into a much more manageable format. A list of query string and total frequency over that week.
Ah, so they transform the raw event stream into a clean frequency map.
Exactly. This aggregation step might still result in gigabytes or maybe low terabytes of data, but it's vastly smaller and cleaner than the raw logs.
All right, we have our aggregated frequency data for the week. Who takes it from there?
This gets handed off to the workers. These are the real workhorses of the offline pipeline. Think of them as a fleet of servers running asynchronous jobs.
And their job is?
Their sole task is to take that aggregated frequency data and build the complete optimized trie data structure from scratch every week.
This is where the magic happens. They insert every unique query string into the trie.
Update the frequency counts.
And crucially, as they build it, or maybe after it's built, they have to compute those cached top lists for every single node in the trie.
Exactly. That's the really computationally intensive part. As they build upwards, or maybe in a separate pass, they need to look at the top lists of a node's children, merge them, sort them, potentially fetch frequencies, and figure out the correct top list for the parent node itself.
That sounds like a pretty heavy recursive calculation, especially near the root of the trie. Must take a while.
It definitely can. Depending on the size of the data set and the number of workers, building the full trie might take several hours.
But it's okay because it's happening offline, in the batch process. It's not impacting the live query service serving users.
Precisely. The users never see this build process happening. Once the workers finish constructing this perfect, optimized, O1-ready trie, it needs to be stored somewhere. The query service can access it instantly.
Which brings us to the final storage layers. We need somewhere fast and somewhere persistent, right?
Exactly. First, the fast layer, the trie cache. This is typically a distributed in-memory caching system. Think Redis, Memcache, something similar.
Distributed meaning it runs across many servers.
Yes, because the trie, especially with a cached list, is likely too big to fit in the RAM of a single server. So we spread it across a cluster of cache servers. The goal is to keep the entire trie structure loaded in RAM.
Why RAM?
Because RAM access is incredibly fast, orders of magnitude faster than disk. This ensures that when the query service needs data for a prefix, it's almost always an in-memory lookup, which is essential for hitting our 100 meters target. The workers basically finish building the trie and then upload a snapshot of it directly into this distributed cache cluster.
Okay, so the live query service primarily talks to the trie cache, but we need persistence too, right? What if the cache servers restart or lose data?
Absolutely. We need a TRIDB, a persistent storage layer. This is where the workers store the definitive canonical version of the weekly trie build. It serves two purposes: long-term storage and recovery, and providing data to the cache if there's a cache miss.
What kind of database works well for storing a complex structure like a trie? It's not exactly relational data.
Good question. Two common options here. One is to use a document store, like MongoDB. You can basically serialize the entire trie object, maybe shard by shard, into a binary format like a BSON document, and just store those blobs. Retrieving it means deserializing the blob.
Okay, stored as a big chunk. What's the other option?
The other option, which can be very efficient, is to map the trie structure onto a key value store, like Cassandra or DynamoDB.
How does that work? A trie is a tree, a key value store is flat.
It's actually quite elegant. Remember how every node in the trie corresponds to a unique prefix path from the root?
Yeah.
We can use that prefix string itself as the key in the key value store. The value associated with that key would be the data payload of the trie node, its frequency, if it's a word, any flags, and most importantly, its pre-computed top list.
Ah, so you flatten the tree by making each prefix path a key. Inter becomes a key, and its value holds the international list.
Exactly. This essentially turns our complex tree into a potentially massive but very efficient distributed hash map lookup in the persistent store. It makes fetching individual node data, like during a cache miss, quite efficient. Hashtag query service optimizations and maintenance.
Okay, great. We have the super fast query service talking to the trie cache and the weekly data pipeline feeding it. Let's tighten things up. How does the query service flow look now? And what about resiliency and other optimizations? Hashtag tag the improved query service flow.
Right, so the optimized request path is now super short and direct. A user types a character, the client sends the current prefix.
That hits a load balancer first, presumably?
Always. Load balancer spreads the requests across a fleet of stateless API servers. The main job of an API server, upon receiving a prefix like into, is to query the trie cache.
It asks the distributed cache, give me the data for key into.
Precisely. And because we designed the trie cache for O1 lookup.
Bam. The API server gets back that pre-computed list, internet, 5,000 international, 1,000, almost instantly. It formats it and sends it back to the client.
That's the happy path. Happens 99.9% of the time. But we need to plan for the unhappy path. What happens if, say, the specific cache server holding the data for inte just crashed? Or maybe its memory got flushed for some reason? A cache miss?
Right. We can't just fail the request or wait minutes for the server to come back. That violates the 100 meters rule badly.
So we need a robust cache miss policy. When the API server asks the trie cache for inte and gets nothing back, a miss, it doesn't give up. Instead, it immediately turns around and queries the persistent TRIDB.
It asks the key value store or document store for the data associated with inte.
Correct. It fetches the data from the persistent storage. Now, this lookup will be slower than the cache hit, maybe taking tens or even hundreds of milliseconds. But here's the crucial part. Once the API server gets the data from the DD,
It serves it to the user.
yes, but before, or maybe while doing that, it also writes that data back into the trie cache. It replenishes the cache.
Ah, so it fixes the cache for the next person who searches for inte.
Exactly. The goal is self-healing. We might slightly exceed the 100 meters budget for that one unlucky user who triggered the miss and had to wait for the DB lookup. But by immediately repopulating the cache, we ensure that the thousands of subsequent requests for that same popular prefix hit the fast RAM cache again. We prioritize overall system availability and performance over the occasional brief latency spike for one user.
Makes sense. Sacrifice one request's latency to protect the next 10,000. Hashtag client-side optimizations for speed.
So we've optimized the backend path heavily, but we can still squeeze out more performance, or at least perceived performance, by optimizing things on the client side right in the user's browser.
What can we do there?
Well, the foundational technology for web-based autocomplete is AJX, requests asynchronous JavaScript and XML, though nowadays it's usually JSON.
Right. This allows the web page to send that prefix request in the background.
Without freezing up the UI or requiring a full page reload every time you type a character. The user can keep typing smoothly while the requests are flying back and forth asynchronously. It's essential for that fluid, instant feeling.
Okay, AJX is table stakes. What else?
The simplest and often most effective client-side optimization is good old browser caching.
Caching the suggestions themselves in the browser.
Absolutely. Remember, our main try only updates once a week. The suggestions for Inte are probably going to be the same today as they were yesterday, and maybe even an hour from now.
So if I type DIN, get suggestions, then maybe backspace and type DIN again a few minutes later.
The browser shouldn't even need to send a request to your servers the second time.
Yeah.
If the results are cached locally, the browser can just pull them from its own cache instantly. Zero network latency.
Nice. How long would we typically tell the browser to cache these results for? It can't be forever, but maybe not too short either.
Yeah, it's a balance.
Yeah.
Looking at what big players do, Google, for instance, often caches autocomplete results for about 3,600 seconds.
That's 1 hour.
1 hour. This is controlled using HTTP headers, specifically the cache control header sent back with the suggestion response. We'd likely send something like cache control, private, max age 3,600.
Why private?
Private tells any shared caches along the way, like maybe corporate proxies or ISP caches, not to store this response. This is generally good practice for potentially user-specific data, even if our current system isn't personalized. It ensures only the end user's browser caches it. Max age 3,600 tells the browser it can reuse this data for the next hour without asking again. Saves bandwidth, saves server load, feels faster. Win, win, win.
Okay, we know the try is built weekly by the workers. We prefer the wholesale replacement method, just swap the old try for the new one and the cache in DB. But let's briefly revisit why trying to do individual node updates is so problematic, just in case we ever thought about it.
It really comes down to that O1 optimization, the cached toplets on every node.
Yeah.
Let's say some obscure query artisanal widget polisher suddenly goes viral and his frequency count skyrockets. Updating the frequency count on the final node for that query is easy. But now, that node's parent, maybe the node for artisanal widget, needs to check. Does this newly popular query now break into my top 5 list?
And if it does,
If it does, the parent node has to update its cached list. But then its parent, artisanal widget, has to do the same check. Does this change from its child affect its top 5 list?
oh man, it cascades all the way up the tree to the root. A single frequency update deep down could potentially trigger updates on dozens of ancestor nodes.
Exactly. It creates this complex, cascading update path involving reads, calculations, and writes on potentially many nodes for a single incoming change. This introduces significant logging challenges and computational overhead, making it incredibly inefficient and difficult to scale under high write load. It would likely interfere with the fast read performance we need.
So, yeah, stick to the weekly wholesale replacement. Much simpler, much cleaner operationally.
Definitely the preferred approach for this kind of system. Now, the last piece is dilution and filtering. Sometimes we need to remove a suggestion immediately, not wait a week. Think unwanted suggestions, hateful, violent, sexually explicit, maybe dangerous misinformation.
Right. Policy violations. We can't have those showing up in autocomplete even for a few hours, let alone a week.
Correct. This requires a different mechanism than the weekly build. It's really a policy enforcement layer. We introduce a dedicated filter layer.
Where does this sit?
Strategically, it sits right in front of the try cache, or perhaps as part of the API server logic, before it even queries the cache. This filter layer maintains a dynamic list, often called a denial list or block list, of forbidden terms or patterns.
So when the API server gets the top 5 suggestions back from the try cache,
It runs them through the filter layer before sending them to the user. The filter layer quickly checks if any of the suggestions match the denial list. If one does, it's simply stripped out of the results. Maybe we return only 4 suggestions, or maybe we try to fetch the 6th best from the cache DB to replace it, though that adds complexity.
okay, so that handles immediate blocking. The user never sees the bad suggestion. But it's still technically in the try cache and try DB, right? It'll come back next week if we don't remove it permanently.
A good point. So the filtering is the immediate stopgap. In parallel, when a term is added to the denial list, we also trigger an asynchronous process. This background job goes and physically removes the unwanted term from the underlying persistent storage, the TryDB, and potentially the source analytics logs, or marks it for exclusion.
So it won't be included in the next weekly try build.
Exactly. Immediate blocking via the filter layer, permanent removal via the asynchronous cleanup job, layer defense, hashtag tag scaling, and future complexities.
All right, we have a really solid, fast system design now. It works great, assuming the entire optimized try fits onto our cache cluster. But what happens when even the distributed cache isn't big enough? When the try, with all its cache lists, grows into many, many terabytes, we need to scale the storage itself. Hashtag scaling the trie storage. Sharding.
Yeah, eventually even a large cache cluster might hit its limits. When the trie becomes too massive for the available RAM across the cluster, we have to resort to sharding the trie itself.
Sharding means splitting the data across different sets of servers.
Exactly. We partition the trie so different subsets of nodes live on different independent cache clusters or server groups. The most obvious naive sharding strategy would be simple alphabetical splitting.
Like server group 1 handles all prefixes starting with A through M, server group 2 handles N through Z, or maybe AE, FJ, etc. if you have more shards.
Right, you just divide the alphabet up evenly. Simple to implement.
But I sense a but coming. This immediately runs into the problem of imbalance, doesn't it?
Absolutely. We talked about this earlier with query distribution. Language is not uniform.
Way more searches start with S or C in English than start with X or Q.
Exactly. So if you use that naive alphabetical split, the shard handling S might be getting absolutely hammered, running hot, struggling to keep up with maybe 40% of the total traffic. Meanwhile, the shard handling X is sitting there bored, basically idle.
Total waste of resources and a violation of our availability goals.
Okay.
If the S shard melts down, a huge chunk of searches fail. We need smarter sharding.
We do. We need to move away from sharding based on character ranges and instead shard based on expected query volume.
How do we manage that? It sounds more complex.
It requires an extra piece of infrastructure, a shard map manager. This is essentially a lookup service, maybe a small database or configuration service that maintains the mapping between prefixes and the physical shard that owns them.
And how does it decide on the mapping?
It needs to analyze the historical query distribution data, the same data used by the aggregators. Based on that analysis, it figures out prefix boundaries that result in roughly equal query volume per shard.
So instead of AM and Z, the shard map manager might look at the data and say, okay, prefixes A through K account for about 30% of queries. Let's put them on shard 1. Prefixes A through R are another 35%. They go on shard 2. The prefix alone is 20%, so else gets its own shard 3. And then A through U's together make up the last 15%. They can share shard 4.
Precisely that kind of logic. You dynamically partition the prefix space based on observed traffic patterns to ensure each shard receives a balanced load. When an API server gets a request for C, it first asks the shard map manager which shard owns S. The manager replies shard 3, and the API server then directs its trie cache query to the servers in shard 3.
Much smarter. Prevents hot shards, ensures even load distribution, keeps us hitting that 100 meters target reliably across the whole system, no matter what the user types. Hashtag handling internationalization and real-time trends.
Okay, so our system is now scalable, sharded, fast for English lowercase letters. What about going global? Multi-language support, supporting Japanese, Arabic, Russian, etc. What's the fundamental change needed in the trie itself?
The nodes can't just hold on through Z anymore.
Exactly. We absolutely must move from basic ASCII or Latin character sets to using Unicode characters within the trie nodes. Unicode is the global standard that provides a unique code point for essentially every character in every major writing system used worldwide.
So a node representing a prefix might now need to handle children corresponding to Cyrillic characters or kanji or Arabic letters.
Correct. This can significantly increase the potential branching factor, number of children for each node, and thus the complexity and memory footprint of the trie. But it's non-negotiable for internationalization. The core trie logic remains the same, but the character set expands dramatically.
Makes sense. And what about geographical differences in popularity? The top searches in Germany are likely very different from the top searches in Brazil.
Right. You can't serve a single global trie based on worldwide popularity and expect it to be relevant locally. The solution here is to build different tries for different regions or languages.
So a German trie built from German logs, a Brazilian Portuguese trie from Brazilian logs, and so on.
Exactly. You segment your data gathering and trie building process geographically or linguistically. And then, to ensure low latency everywhere, you need to deploy these localized tries intelligently. You leverage content delivery networks, CDNs. You place copies of the relevant regional trie data, or the specific shards needed for that region using our smart sharding, onto CDN edge servers located physically close to users in those regions.
So a user in Seoul hits a CDN server in Korea that holds the Korean trie data. A user in Paris hits a server in Europe with the French trie, minimizes network latency.
Precisely. Geo-localized tries deployed via CDN edge locations.
Okay, final challenge. The really tough one. The one that kind of breaks our beautiful weekly batch model. Trending queries. What happens when a major news story breaks, or a celebrity does something shocking, or a meme explodes, and suddenly millions of people are searching for something nobody searched for yesterday? Our weekly try is a week out of date.
This is where the batch processing model fundamentally falls short. It's great for stable, long-term popularity, but terrible for reacting to sudden, ephemeral spikes. Handling real-time trends requires moving beyond batch entirely, at least partially. We need a parallel, real-time streaming pipeline.
Okay, so we don't replace the batch system, we augment it.
Usually, yes, you keep the weekly build for the stable historical baseline, but you add a new system that processes incoming queries as they happen.
How does that work? What technologies?
This involves stream processing platforms. Think things like Apache Kafka for ingesting the real-time query stream, and then Apache Flink or Spark streaming for processing that stream continuously.
And what does this streaming pipeline produce? Does it try to update the main try?
No, we learned that's too hard. Instead, it typically builds a separate, much smaller, much more lightweight index. Let's call it the trending index. This index only tracks query frequencies over a very short, recent time window, maybe the last 15 minutes or the last hour.
So it only knows about very recent activity.
Exactly. It's small, volatile, and focused purely on what's hot right now. Then, the crucial step is changing the ranking model in the query service.
How?
When the API server gets a prefix, it now queries both the main historical try-cache and this new trending index. It gets two sets of suggestions, potentially overlapping. It then needs logic to merge these lists, giving significantly more weight to queries that are currently trending, even if their historical frequency is low.
So a query that just exploded in the last 10 minutes might jump into the top 5, displacing a historically popular but currently less relevant query?
Precisely. The final list presented to the user becomes a dynamic blend. It leverages the stability and depth of the historical data, but overlays the immediate relevance of real-time trends. That combination is how you get suggestions that feel both solid and up to the minute. #tagatro.
Wow. What a journey indeed. He started with this seemingly impossible problem, 48,000 peak queries per second, each needing an answer in under 100 milliseconds. A standard database approach was, as you said, dead on arrival.
Completely infeasible.
But step by step, we architected a solution. We landed on the try data structure. We made that crucial, expensive trade-off, sacrificing potentially terabytes of memory to cache the top K suggestions on every single node.
All to achieve that constant time, O1, lookup performance. Non-negotiable.
Then we designed the offline weekly batch pipeline with workers diligently building this massive optimized structure fed by aggregators processing potentially sampled logs. We figured out persistent storage using document or key value stores and the critical role of the in-memory try-cache.
We layered on resilience with cache miss policies, client-side optimizations like browser caching, and robust filtering for policy enforcement. And we addressed scaling through smart, volume-based sharding managed by a shard map manager.
And finally, we tackled the global scale with Unicode and CDNs and the tough challenge of real-time trends by augmenting our batch system with a parallel streaming pipeline and a blended ranking model.
It really highlights that central conflict in designing these massive autocomplete systems, doesn't it? It's this constant tension between serving stable, reliable, historical popularity, which is best handled by batch processing and reacting instantly to breaking, unpredictable real-time events which demand stream processing.
Yeah, the historical view versus the instantaneous view.
So here's a final thought for you listening. As you type your next search query and see those suggestions appear, think about what you actually want in that moment. Do you want the query that was most popular overall for the past year? Or do you want the query that just exploded onto the scene 5 minutes ago because of a major news alert?
That's a really interesting question. It probably depends heavily on the context of the search, right?
Exactly. And how the system designers chose to balance those two priorities, historical stability versus real-time relevance, fundamentally shapes the performance, the feel, and even maybe the perceived intelligence of the search engine you're using.
Definitely something to ponder, a deep dive for perhaps another time. For now, thanks so much for walking us through that really fascinating stuff.
My pleasure. It's a great system design challenge.
And thanks to all of you for joining us on the deep dive. We'll see you next time.